Hi guys, today we're going to learn some of section 5.3. We're not going to get through the whole section of the book in one lesson, but we're going to do some of it. So today, one of our objectives is we want to be able to calculate the probability of compound events that are independent and are dependent. So here's the key. This is when it's two or more events. Okay. Before, when it was A or B, that was select one. Select one person, select one item, pick one, whatever. Okay, now it's going to be like there's different ways that it can happen. So it can either be that this happens and then that happens, or you pick this and then you pick that. So it could be what's the probability that you wake up late and you miss the bus? All right, instead of just wake up late or miss the bus. Okay, so it's wake up late and then you also miss the bus. Independent events, we know from all the other kinds of things, it's when one doesn't affect the other. They're separate, they're independent from each other. Dependent events are when the occurrence of one event influences or changes the probability of the next event occurring. You have to make this decision. When you read a problem, you have to decide, does the context of the problem make it independent, or does the context of the problem make the events dependent? No matter what, if it's you do this and then you do that, you're going to multiply. Okay? So if it's the A happens and then B happens, probability of A times probability of B. If they're independent, you can just multiply the two probabilities together. All right? It also applies to any time that there's replacement. We'll do a marble problem in a minute, and I'll go over that then. If you have dependent events, then the probability of A and then B happening is that the probability that B occurs in the first trial and A occurs in the second trial, knowing that B already happened. So if I'm picking if there's 10 names in a hat, and there's 5 boys, 5 girls, and I say, what's the probability of picking 2 boys in a row? Well, if I pick the first boy, then the first boy would be 5 out of 10. But then the second probability is going to be affected by what happened in the first problem. So it would be 4 boys left and 9 kids total if I don't replace their names. So then it would be 5 over 10 times 4 over 9. That's dependent probabilities. All right. The notation that you use, this formula, neither of these is on your formula card. There is a version of this that we're going to get to later, okay? But it's not in this setup. But we would read this. This is a vertical bar. It's not a fraction. It's a vertical line, and it's called given that. So I would read this as A given that B happened. So like, what's the probability of A happening given that B already happened? All right. So before we do examples 1 and 2, I want to do example 3. I'm going to go a little out of order. So let's start super generic with marbles. All right, because you've been working on them forever. 30 marbles in the bag, 10 red, 12 white, 8 blue. We want to find the probability of selecting a red marble and then a red marble with replacement. So with replacement means they're independent events. The probability of one doesn't change the other. The first, we would have probability of red, and then red is probability of red times probability of red. Probability of red marble, 10 out of 30. Probability of a red marble, 10 out of 30 because it got replaced. That's a third times a third. So my answer is 1/9. Okay. But if I do a slight change in the word problem, I say without replacement, then it's still going to be probability of red, but then it's going to be probability that the second is red, given that the first was red. I'm going to put a 1 here. So probability that the first was red was 10 out of 30. Now keep in mind, this is not a fraction. This is just a way of saying what's probably that the second is a red if we already know that the first was a red. Which means that if a red marble was picked, instead of 10 being in the bag, there's 9. And if a marble was picked, then there are 29 left over. Okay, so then you can solve. What do you get? 1/3 divided by 3. I think it's 3/29 as your answer. Okay. Pardon me if I do my fractions wrong in my head. So here we go, a red, a blue, and then a white with replacement. So the probability of a red, and then multiply the probability of a blue, and then multiply probability of a white. Probability of red is going to be 10 out of 30. With replacement means there's still 30. You put it back. Blue marbles, 8. White, put it back, 12, 30. I'm not going to do this in my head right now. Whatever you get, you get. Okay, it's fine. Like your actually, let me just show you guys to make sure you're good to go with the calculator part. Just hit the fraction button, right? So then you're going to have 10 out of 30. Go to the right, times, hit the fraction button, control divide gets you a fraction, 8 out of 30. Go to the right, times, little fraction button, 12 out of 30. Press enter, boom. It multiplies for you and simplifies. 8 out of 225. You can switch these over to decimals as well if you want. Now, without replacement, you got to think, because red is going to be 10 out of 30. Now, we're switching to blue. There are still 8 blue marbles because no blues have been chosen yet, but there's only 29 left. There's still 12 white because no whites have been chosen yet, but now there's only 28 marbles left. Okay, so this time up here, it was red, then red, so the numerator changed as well, but this time it's red, then blue, then white. So the numerator isn't changing, it's just the denominator. If I go grab these and just change this to 28 and change this to 29, you get 8 out of 203. Okay, what's our probability of selecting a red or a blue marble? Well, or means add. Red or blue. Are these overlapping categories? No, they are not. So you're going to have red plus blue. You're going to get 18 out of 30. And then you're going to simplify that. And what do you get? Divide by 6. 3/5. Done. Okay. Now, this is more how you see it in Algebra 2. Okay. We're going to talk about a bunch of different stuff. So, with baseball, a perfect game is when the pitcher doesn't allow any hitters to reach the base in all 9 innings. So there's no one gets on base for the entire game. Historically, pitchers throw a perfect inning, an inning where no hitters reach the base about 40% of the time. So the probability of a perfect inning is 0.40. To throw a perfect game, the pitcher needs to have 9 perfect innings in a row. What's the probability that a pitcher throws 9 perfect innings in a row, assuming that the pitcher's performance in an inning is independent of his performance in other innings, which means they're not affecting each other? So to get 9 perfect innings, be really careful. It's not 9 times 0.40. It's the probability that the first is perfect, and the second is perfect, and the third is perfect, all the way up to the 9th is perfect. So it's 9 of these multiplied together. So it's 0.4 times 0.4 times 0.4 and so forth, all the way up to the 9th 0.4. Okay, so really the probability of 9 perfect innings can be found by doing 0.4 to the 9th power. All right, if you multiply by 9, you're going to get 3.6, which is impossible because that would be greater than 1, and that's not a true number, okay, for probability. When you multiply this 0.4 to the 9th power, you're going to get 0.00026, and that's your answer, okay? If you're not careful, I wonder if my calculator would do it or if I have my settings. 0.4 to the 9. Yeah, okay, cool, it did it. This E here means scientific notation. So this is the same as saying 2.62 times 10 to the negative 4.